Imagine standing at the edge of our world, not at a coastline where land meets water, but at the cosmic precipice where our galaxy meets the vast, uncharted depths of intergalactic space. You gaze outward, beyond the familiar stars, into a darkness so profound it seems to pull at your very soul. Picture this. You've somehow acquired a spacecraft capable of traveling beyond our solar system, beyond our galaxy, and into the cosmic void that exists between island universes. What would you see as the Milky Way shrinks behind you? What lies in the emptiness between galaxies? This seemingly simple question conceals one of astronomy's most haunting mysteries. The farther we look outward from Earth, the deeper into the past we peer, revealing a universe that doesn't quite align with our expectations, a cosmos that challenges our understanding of space, time, and our place within it. Tonight, we embark on a journey few have contemplated. What happens if you keep traveling away from the Milky Way? The answer reveals secrets about our universe that most people will never know. Cosmic truths that reshape our understanding of reality itself. The stars above us tell ancient stories. For millennia, humans have looked upward and wondered about our place among them. But only recently have we begun to comprehend the true scale of our cosmic neighborhood and what might exist beyond its boundaries. Our Milky Way, a spiral galaxy spanning 100,000 light-years, houses hundreds of billions of stars, countless planets, and innumerable possibilities for life. Yet, it represents merely a single pixel in the cosmic portrait, a lone island in a sea of galaxies stretching beyond our imagination. What happens when we leave this island? What strange phenomena await in the spaces between galaxies? What might we discover about the nature of the universe itself as we travel farther from the familiar shores of our cosmic home? These questions have fascinated astronomers, physicists, and dreamers throughout human history. The answers challenge our perception of reality and invite us to reconsider what we know about the cosmos and our place within it. As we drift away from our galaxy, the very fabric of space reveals itself in ways impossible to observe from Earth. The mysteries of dark energy, cosmic expansion, and the ultimate fate of the universe become tangible realities rather than abstract theories. Our journey begins with a simple thought experiment, a cosmic ship sailing away from our galactic harbor. But this thought experiment quickly transforms into a profound exploration of the universe's deepest mysteries and humanity's eternal quest to understand them. The night sky appears static to our naked eyes. Stars seem fixed in their celestial positions, creating the illusion of permanence. But this perceived stillness masks a universe in constant motion, expanding, evolving, and changing over timescales that dwarf human existence. What if we could witness this cosmic evolution directly? What if we could observe the changes not over billions of years, but through a journey of our own making? What would the universe reveal to us as we venture beyond our galactic boundaries? Perhaps more importantly, what would this journey teach us about ourselves? About our significance or insignificance in the grand cosmic tapestry? About the unique conditions that allowed our existence in this particular corner of space and time? Tonight, we will explore these questions. We will travel beyond the familiar spiral arms of our galaxy, past the local group of galaxies, through the vast cosmic web of galactic superclusters, and into the most mysterious regions of our observable universe. Our journey will reveal not only what exists beyond our galaxy, but also how these distant realms shape our understanding of existence itself. It will challenge our perception of what it means to be human in a universe of almost incomprehensible scale. The stars you see in the night sky belong to our galaxy. Even with the most powerful telescopes, individual stars in other galaxies remain indistinguishable points of light. What would it mean to leave behind all the stars we've ever known? As we depart the Milky Way, familiar constellations dissolve. Orion's belt untangles. The Big Dipper's handle bends out of shape. The night sky transforms from a dome of scattered light to a cohesive spiral structure, our galaxy viewed from the outside. What emotions might stir within you as you witness our cosmic home shrinking in your spacecraft's rear viewport? Would you feel an existential emptiness or a profound connection to something greater than yourself, perhaps both simultaneously? Throughout this voyage, we'll encounter cosmic phenomena that challenge our understanding of physics, vast voids where galaxies fear to tread, invisible threads of dark matter binding the universe together, and the mysterious force driving the cosmos apart at ever-increasing speeds. Our journey outward from the Milky Way is simultaneously a journey inward, toward deeper understanding of our origins, our nature, and our potential futures. The farther we travel from home, the more clearly we see what home truly means. This contemplative expedition reveals not just the external universe, but also the universe within, the atomic connections linking our bodies to stars, our thoughts to cosmic evolution, and our existence to the grand story of the cosmos itself. Tonight, we will confront the sublime beauty and terrifying scale of our universe. We will face the cosmic horizon where space expands faster than light can travel, creating boundaries beyond which we can never observe or reach. Join me as we embark on this impossible journey, a voyage not of the body but of the mind, imagination, and scientific understanding. Together, we'll explore what happens when we leave everything familiar behind and sail into the cosmic unknown. Chapter 2: The Meaning of Cosmic Wandering. Why does this journey matter? The question of what lies beyond our galaxy might seem academic, a thought experiment with little relevance to our daily lives. Yet throughout human history, our understanding of the cosmos has profoundly shaped our sense of self. When Copernicus revealed Earth was not the center of the universe, he didn't just reposition our planet. He transformed humanity's perception of its place in creation. When Edwin Hubble proved that galaxies exist beyond the Milky Way, he expanded our cosmic neighborhood into an unimaginably vast metropolis. Each revelation about our universe has rippled through human culture, philosophy, and self-understanding. Our journey beyond the Milky Way continues this tradition, challenging us to reconsider our significance in an expanding cosmos that grows more mysterious with each discovery. There's something deeply comforting about contemplating cosmic scales. Our daily troubles, deadlines, relationships, financial worries, shrink when viewed against the backdrop of galactic superclusters and billion-year timescales. This cosmic perspective offers a unique form of solace. Yet this comfort comes with a paradox. The same cosmic perspective that diminishes our individual importance also highlights the extraordinary improbability of our existence. We are made of atoms forged in stellar furnaces, arranged into consciousness capable of contemplating its own origins. Our journey outward from the Milky Way serves as a meditation on this paradox. As we conceptually leave our galaxy behind, we gain distance not just in space, but in perspective, seeing our existence from a vantage point that reveals both its fragility and its wonder. Consider what it means that you exist in this particular galaxy, on this particular planet, at this particular moment in cosmic history. The conditions that allowed for your existence require billions of years of cosmic evolution, from the formation of heavy elements to the emergence of life. Had the universe's fundamental constants been slightly different, had our galaxy formed with a different structure, had our solar system occupied a different position within it, you might never have existed to contemplate these very questions. This cosmic context doesn't diminish the meaning of human experience, it enriches it. Understanding our place within the universe's grand narrative adds layers of significance to our brief moments of consciousness, our connections with others, and our search for purpose. Our imaginary journey beyond the Milky Way isn't about escaping our reality, but about seeing it more clearly. Like astronauts who return from space with a transformed perspective on Earth, we return from our cosmic voyage with fresh eyes for our galactic home. Throughout human history, we've defined ourselves through boundaries: geographical, cultural, conceptual. What happens when we transcend the boundary of our own galaxy? What new self-understanding emerges when we conceptualize ourselves as cosmic citizens rather than merely terrestrial ones? This shift in identity has already begun. When we speak of our galaxy, we're acknowledging membership in a community that transcends national, ethnic, and even planetary divisions. We're claiming kinship with all that exists within this spiral structure of stars, dust, and dark matter. Venturing beyond our galaxy extends this perspective further. It invites us to consider our relationship not just to our immediate cosmic neighborhood, but to the universe as a whole, to contemplate our connection to distant galaxies and the mysterious spaces between them. This expanded identity doesn't erase our human connections. It nestles them within progressively larger contexts: family, community, nation, planet, solar system, galaxy, galactic group, supercluster, and beyond. Each level adds dimension to our understanding of who and what we are. There's a profound humility in recognizing our place within this cosmic hierarchy. The Milky Way contains hundreds of billions of stars, many with their own planetary systems. Our Sun is but one star, our Earth, one planet, humanity, one species among countless life forms. Yet this cosmic humility needn't lead to nihilism. The same universe that dwarfs us physically has produced, through us, the capacity to comprehend itself. In our consciousness, the universe has developed a way to witness its own grandeur and contemplate its own meaning. As we journey beyond our galaxy, we carry this consciousness with us, this uniquely human blend of curiosity, wonder, and meaning-making. Our physical bodies may never make this journey, but our minds can traverse these cosmic distances through science and imagination. This mental voyage transforms not just how we see the universe, but how we experience our lives within it. Everyday moments, watching a sunset, holding a loved one's hand, contemplating a starry night, take on additional significance when viewed against the cosmic backdrop. The forest seen from within appears as individual trees. Seen from above, it reveals patterns invisible at ground level. Similarly, our lives viewed solely from within may seem random or disconnected. The cosmic perspective reveals the extraordinary patterns that make our existence possible. Our journey away from the Milky Way reveals the cosmic web, a structure where galaxies cluster along filaments, separated by vast voids. This cosmic architecture echoes patterns we see throughout nature, from neural networks to social connections, suggesting a universe that tends toward complexity. In contemplating what lies beyond our galaxy, we discover something profound about the nature of human consciousness. We can transcend our physical limitations through curiosity and imagination. We can conceptually occupy viewpoints impossible for our bodies to reach. This capacity for transcendence defines us. We are physically bound to Earth, yet mentally capable of exploring the farthest reaches of the observable universe. We are temporally limited, yet able to comprehend timescales spanning billions of years before and after our existence. When we ask what happens as we leave the Milky Way behind, we're engaging in an act unique to human consciousness, projecting ourselves beyond our immediate surroundings, beyond our direct experience, into realms accessible only through mathematical models and scientific inference. This projection isn't merely an intellectual exercise. It's a profound expression of what makes us human, our need to contextualize our existence within something larger than ourselves, to understand our place in a cosmos whose full dimensions exceed our direct perception. Chapter 3: The Dawn of Cosmic Awareness. Our journey beyond the Milky Way begins, paradoxically, with humanity's earliest attempts to understand the night sky. Ancient civilizations across the globe, from Mesopotamia to China, from Egypt to Mesoamerica, developed sophisticated systems for tracking celestial movements. These early astronomers couldn't know they were observing a galaxy, much less contemplate what lay beyond it. To them, the night sky was a celestial dome adorned with fixed stars, wandering planets, and occasional comets. a cosmic clockwork intimately connected to terrestrial events. The ancient Greeks made remarkable strides in astronomical thinking. Aristarchus of Samos proposed a heliocentric model of the solar system in the 3rd century BCE, while Eratosthenes calculated Earth's circumference with surprising accuracy using nothing more than shadows and geometry. Yet even these advanced thinkers couldn't conceive of a universe containing billions of galaxies. Their cosmos remained finite and incomprehensible, a series of nested spheres with Earth at the center and the fixed stars adorning the outermost shell. This geocentric model persisted for nearly 2 millennia, reinforced by religious doctrine and apparent common sense. After all, doesn't the sun clearly move across our sky? Doesn't the Earth feel solid and stationary beneath our feet? The truth would prove far more wonderful. The Copernican revolution of the 16th century marked humanity's first significant step toward understanding our true cosmic position. By placing the sun at the center of our planetary system, Copernicus began the process of displacing Earth from its privileged central position. This decentering continued with Galileo's telescopic observations in the early 17th century. His discovery of Jupiter's moons and the phases of Venus provided compelling evidence for the Copernican model, suggesting that Earth was indeed one planet among several orbiting the Sun. Giordano Bruno went further, proposing in the late 16th century that the stars were distant suns, potentially orbited by their own planets. This radical idea, that our solar system might be one of countless similar systems, cost Bruno his life but anticipated our modern cosmic understanding. Isaac Newton's laws of motion and universal gravitation, published in 1687, provided the physical principles governing celestial bodies. The universe was no longer moved by divine whim or perfect spheres, but by mathematical laws that applied equally to falling apples and orbiting planets. By the 18th century, astronomers recognized that the hazy band of light stretching across the night sky, what we now call the Milky Way, consisted of countless individual stars. Our cosmic home was beginning to reveal itself, though its true nature remained elusive. The first serious attempt to comprehend the Milky Way structure came from William Herschel in the late 18th century. By carefully counting stars in different directions, Herschel created a map placing our solar system near the center of a disc-shaped collection of stars. Herschel's model, though incorrect in its centralized positioning of our Sun, represented the first systematic attempt to map our galaxy. He also identified numerous nebulae, fuzzy patches of light that would later prove crucial to understanding what lies beyond our galactic borders. Throughout the 19th century, increasingly powerful telescopes revealed more of these nebulae, sparking debate about their nature. Were they gas clouds within our galaxy? Or might they be distant island universes, separate galaxies like our own Milky Way? This great debate culminated in a famous confrontation between astronomers, Arlo Shapley and Heber Curtis, in 1920. Shapley argued that the Milky Way encompassed the entire universe, while Curtis maintained that spiral nebulae were distant galaxies comparable to our own. The debate wasn't merely academic. At stake was nothing less than the scale of the universe and humanity's place within it. If Curtis was right, the cosmos was vastly larger than anyone had imagined, and our galaxy was just one among countless others. Meanwhile, theoretical physics underwent its own revolution. Einstein's theories of special and general relativity, published in 1905 and 1915 respectively, transformed our understanding of space, time, and gravity, the fundamental fabric of the universe through which our cosmic journey would take us. Einstein's equations suggested something remarkable. The universe might be expanding. This possibility emerged from his field equations of general relativity, though Einstein himself initially rejected this interpretation, introducing a cosmological constant to maintain a static universe. The stage was set for a profound discovery, one that would definitively resolve the great debate and forever change humanity's understanding of the cosmos. All that remained was for someone to gather the observational evidence that would reveal what truly exists beyond our galaxy. That someone was Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California. In 1924, Hubble identified Cepheid variable stars in the Andromeda Nebula, stars whose intrinsic brightness made them reliable cosmic yardsticks. By measuring these stars, Hubble determined that Andromeda lay far beyond the boundaries of the Milky Way, too distant to be part of our galaxy. The Andromeda Nebula was, in fact, another galaxy entirely, an island universe similar to our own but separate by a vast cosmic gulf. This discovery effectively ended the Great Debate. Curtis had been right. The universe extended far beyond our galaxy. The Milky Way, once thought to encompass all of creation, was revealed as just one galaxy among billions, opening the door to our journey beyond its boundaries. A few years later, in 1929, Hubble made an even more astonishing discovery. By measuring the spectra of distant galaxies, he found that almost all were redshifted. Their light stretched toward the red end of the spectrum, indicating they were moving away from us. Moreover, Hubble observed that more distant galaxies were receding faster than nearby ones, a relationship now known as Hubble's law. This observation provided the first empirical evidence for an expanding universe, confirming what Einstein's equations had suggested was possible. The implications were staggering. If the universe is expanding, then rewinding cosmic history would show it was once much smaller and denser. This insight eventually led to the Big Bang Theory, the idea that our universe began as an infinitely dense point about 13.8 billion years ago. With these discoveries, humanity's conception of the cosmos was transformed. The universe was not static but dynamic, not bounded but expanding, not centered on our galaxy, but composed of billions of galaxies scattered across an inconceivably vast and growing space. Chapter 4: The Scale of Our Cosmic Neighborhood. To truly appreciate what lies beyond our galaxy, we must first understand the Milky Way itself. Our galactic home is a barred spiral galaxy spanning approximately 100,000 light-years from edge to edge, a distance so vast that light, traveling at 186,000 miles per second, takes a millennium to cross just 1% of it. Our solar system resides in an unremarkable region about 26,000 light-years from the galactic center, nestled within one of the spiral arms. From this vantage point, most of our galaxy remains invisible to the naked eye, obscured by cosmic dust that blocks visible light. The Milky Way contains between 100 and 400 billion stars, though the exact number remains uncertain. If each star were represented by a grain of sand, our galaxy would fill a small bedroom from floor to ceiling, an analogy that still fails to capture its true enormity. Around these stars orbit countless planets. Conservative estimates suggest our galaxy contains at least 100 billion planets, with perhaps 20 billion Earth-like worlds potentially capable of supporting life as we know it. Each represents a unique environment with its own history and possibilities. Yet for all its vastness, our galaxy is just the beginning of our journey. As we conceptually leave the Milky Way behind, the first landmarks we encounter are its closest neighbors, the Magellanic Clouds, satellite galaxies visible from Earth's southern hemisphere as hazy patches in the night sky. These dwarf galaxies orbit the Milky Way like cosmic moons, gradually being torn apart by our galaxy's gravitational pull. Their stars and gas will eventually be incorporated into our galactic home, a cosmic merger playing out over billions of years. Beyond these satellites lies the Andromeda Galaxy, M31, the Milky Way's larger spiral neighbor, located approximately 2.5 million light-years away. Despite this immense distance, Andromeda is visible to the naked eye under dark skies, the most distant object viewable without optical aid. Andromeda and the Milky Way are engaged in a cosmic dance that will culminate in a collision. approximately 4.5 billion years from now. This galactic merger will transform both spirals into a single elliptical galaxy, their once distinct structures blended into a new cosmic entity. Together with Andromeda, the Milky Way, and about 50 smaller galaxies, we form the Local Group, a gravitationally bound collection spanning roughly 10 million light-years. This galactic neighborhood represents our first step beyond our home galaxy into the larger cosmic structure. As we continue outward, we encounter other galaxy groups and clusters, collections of hundreds or even thousands of galaxies bound together by gravity. The nearest major cluster, the Virgo cluster, lies about 54 million light-years from Earth and contains approximately 1,500 galaxies. The Virgo cluster forms the heart of the Virgo supercluster, a vast structure encompassing the Local Group and numerous other galaxy clusters. This supercluster spans approximately 110 million light-years and contains, at least, 47,000 galaxies, a metropolis on a cosmic scale. In 2014, astronomers discovered that the Virgo supercluster is merely one lobe of an even larger structure named Laniakea, meaning immense heaven in Hawaiian. This supercluster complex spans about 520 million light-years and contains approximately 100,000 galaxies. These enormous structures form in response to the invisible scaffolding of dark matter, a mysterious substance that interacts through gravity but not with light. Dark matter filaments create a cosmic web, along which visible matter, stars, gas, and galaxies collects and forms structures. Between these filaments lie cosmic voids, vast regions nearly empty of galaxies, spanning hundreds of millions of light-years. As our journey takes us beyond the Milky Way, we would encounter these eerie domains where galaxies are rare outposts rather than common sights. The largest known void, the Boat's Void, spans approximately 330 million light-years, yet contains only about 60 galaxies. If the Milky Way were located at its center, we wouldn't have discovered other galaxies until the 1960s, fundamentally altering the history of astronomy. As we travel farther from our galaxy, the effects of cosmic expansion become increasingly apparent. Space itself stretches, carrying galaxies away from each other like raisins in an expanding loaf of bread. This expansion accelerates due to dark energy, a mysterious repulsive force permeating the universe. At sufficiently large distances, billions of light-years from the Milky Way, galaxies recede from us faster than the speed of light. This doesn't violate Einstein's theories, because the galaxies themselves aren't moving through space at these speeds. Rather, space itself expands between them. This expansion creates a cosmic horizon beyond which we can never observe. Light from galaxies beyond this horizon will never reach us, no matter how long we wait. The observable universe thus represents only a fraction of what exists, a humbling limitation to our cosmic perspective. Our current observations reveal an observable universe spanning approximately 93 billion light-years in diameter, containing roughly 2 trillion galaxies. Each galaxy hosts billions or trillions of stars, many with their own planetary systems, an almost incomprehensible abundance of cosmic real estate. And yet, the observable universe may be just a tiny pocket within a much larger, perhaps infinite cosmos. Some cosmological models suggest our universe might be one bubble in a vast multiverse, each with potentially different physical laws and fundamental constants. As we stand at this precipice, having journeyed in our minds from Earth to the edges of the observable universe, we face profound questions. What exists beyond what we can see? Does the universe continue infinitely, or does it possess some ultimate boundary? These questions touch the limits not just of our knowledge, but of what can be known. The light from regions beyond our cosmic horizon will never reach us, leaving their nature permanently beyond empirical investigation, a reminder of the boundaries to human understanding. Yet even with these limitations, Our conceptual journey beyond the Milky Way reveals a universe of breathtaking scale and complexity. From our humble position on a small planet orbiting an average star in an ordinary galaxy, we've managed to map the cosmos across billions of light years. This achievement, understanding what lies beyond our galaxy, represents one of humanity's greatest intellectual adventures. It has transformed our cosmic perspective from a universe centered on Earth to one in which our entire galaxy is but a speck in an incomprehensibly vast cosmos. As we prepare to venture deeper into the cosmic unknown, we carry with us this humbling perspective, not as a diminishment of human significance, but as an invitation to appreciate the extraordinary circumstances that allow us to contemplate such wonders from our tiny cosmic home. Chapter 5: Cosmic Conundrums Beyond the Milky Way. As we venture beyond our galaxy's boundaries, the universe reveals perplexing contradictions that challenge our most established theories. What begins as a straightforward journey soon encounters phenomena that defy easy explanation, cosmic puzzles that have left astronomers searching for answers. The first mystery emerges when we examine the rotation of galaxies. According to the laws of physics as we understand them, stars at the outer edges of spiral galaxies should orbit more slowly than those closer to the center, just as distant planets in our solar system orbit the sun more slowly. Yet observations consistently show that stars throughout galaxies orbit at roughly the same speed, regardless of their distance from the galactic center. This flat rotation curve phenomenon suggests galaxies should be tearing themselves apart unless something invisible is holding them together. This invisible something is what astronomers call dark matter, a mysterious substance that doesn't interact with light but exerts gravitational influence. According to current models, dark matter forms a vast halo around galaxies, providing the extra mass needed to explain their rotation. Yet despite decades of searching, no one has directly detected dark matter particles. Some scientists question whether dark matter exists at all, suggesting instead that our understanding of gravity itself might need revision at galactic scales. This controversy intensifies as we move beyond individual galaxies to examine galaxy clusters, collections of hundreds or thousands of galaxies bound by gravity. Here too, visible matter accounts for only a fraction of the mass needed to explain how these clusters hold together. If dark matter doesn't exist, theories like modified Newtonian dynamics, (MOND), propose that gravity behaves differently at vast distances. But these alternative theories struggle to explain all observations across cosmic scales, leaving scientists in an unsatisfying middle ground. The universe is not only stranger than we imagine. Physicist Arthur Eddington famously remarked, "It is stranger than we can imagine." This wisdom becomes increasingly apparent as our journey continues into the spaces between galaxies. In these vast intergalactic voids, we encounter another mystery. The universe appears to be expanding at an accelerating rate. This acceleration defies the expectation that gravity should be slowing cosmic expansion over time, not speeding it up. To explain this acceleration, physicists have proposed the existence of dark energy, a repulsive force permeating all of space. Unlike dark matter, which pulls things together, dark energy pushes things apart, and its influence grows as the universe expands. Combined with dark matter, dark energy presents a humbling reality. Approximately 95% of our universe consists of substances we cannot directly detect or fully explain. The visible universe, all the stars, planets, and galaxies we can observe, represents merely the cosmic tip of an invisible iceberg. This discovery fundamentally altered our understanding of cosmic destiny. Rather than eventually collapsing back on itself in a big crunch or expanding at an ever-slowing rate, our universe appears destined to expand forever, with galaxies accelerating away from each other into cosmic isolation. Yet even this model contains contradictions. Measurements of the universe's expansion rate yield different values depending on the method used. Nearby measurements suggest one rate of expansion, while observations of the distant early universe suggest another. This Hubble tension has persisted despite increasingly precise measurements, suggesting either systematic errors in our observations or, more intriguingly, new physics beyond our current understanding. Perhaps the cosmos changes its expansion rate over time in ways we don't yet comprehend. As we continue outward from our galaxy, another anomaly appears. The universe looks remarkably similar in all directions, even regions so far apart they couldn't have exchanged information since the Big Bang. This horizon problem suggests either faster-than-light communication or an incomplete cosmological model. Cosmologists propose cosmic inflation, an incredibly rapid expansion in the universe's first fraction of a second, to explain this uniformity. But inflation itself raises questions. What caused it? What stopped it? And why did it produce a universe with precisely the properties we observe? The deeper we venture into intergalactic space, the more we encounter the limits of our knowledge. The cosmos becomes increasingly strange, with phenomena that stretch the boundaries of our theoretical frameworks and observational capabilities. Consider galaxy superclusters, vast collections of galaxy clusters that form the largest known structures in the universe. These enormous cosmic architectures trace the invisible scaffolding of dark matter, creating a cosmic web of filaments and voids spanning billions of light years. But here too lies a puzzle. Some structures appear too large to have formed in the time since the Big Bang. The Hercules Corona, Borealis Great Wall, stretching across 10 billion light-years, challenges our understanding of how quickly cosmic structures can emerge and organize. Similarly, the existence of massive, fully formed galaxies in the early universe defies expectations. These ancient cosmic giants appeared too soon after the Big Bang to have grown so large through conventional processes of galactic evolution and star formation. These anomalies don't necessarily invalidate our cosmological models, but they do suggest missing pieces in our understanding, gaps in knowledge that become apparent only when we step back far enough to see the largest scales of cosmic organization. As we journey outward, we also encounter evidence of cosmic collisions and mergers that reshape galactic structures. Galaxy clusters slam together at millions of miles per hour, creating shock waves in the intergalactic medium and distorting the very fabric of space-time. The Bullet Cluster, for instance, provides compelling evidence for dark matter through the separation of visible and gravitational mass after a collision. Yet similar collisions sometimes yield different results, suggesting our understanding of dark matter remains incomplete. Looking deeper into space, and thus further back in time, we observe quasars, incredibly bright galactic cores powered by supermassive black holes devouring surrounding matter. These cosmic lighthouses shine from the universe's distant past, revealing how galaxies evolved over billions of years. Yet some quasars appear too massive too early in cosmic history, challenging our understanding of how supermassive black holes form and grow. The existence of billion solar mass black holes, just a few 100 million years after the Big Bang, suggests processes we haven't yet identified. As we push toward the edge of the observable universe, we encounter the cosmic microwave background radiation, the afterglow of the Big Bang itself. This ancient light reveals temperature variations that seeded the formation of all cosmic structures we see today. While the cosmic microwave background largely confirms our standard cosmological model, it also contains anomalies, unexpected patterns and alignments that some scientists argue are statistically significant. These include a mysterious cold spot that appears larger than predicted by standard models. Are these anomalies mere statistical flukes, observational artifacts, or hints of new physics? The answer remains uncertain, illustrating how our journey beyond the Milky Way takes us not just through space, but through layers of scientific understanding and uncertainty. Perhaps the most profound contradiction emerges when we consider the totality of the observable universe. Our best theories suggest that the laws of physics themselves might vary across cosmic expanses or over timescales beyond our direct observation. The fundamental constants that govern atomic behavior, electromagnetic forces, and gravitational attraction might not be constant at all, but do vary slightly in different cosmic epochs or regions. Slight variations in these values would create universes vastly different from our own. This possibility, that physics itself might be mutable, represents the ultimate cosmic puzzle. If true, it would transform our understanding of reality itself, suggesting our universe represents just one manifestation of physical law in a much larger space of possibilities. As our journey takes us to the very edge of the observable universe, we face the limits not just of our vision, but of what can be known through observation. Beyond this cosmic horizon lie regions forever beyond our reach, their light unable to reach us due to cosmic expansion. What exists beyond this boundary? Does the universe continue infinitely, or does it possess some ultimate edge? Does it curve back on itself in higher dimensions, forming a closed hypersphere with no boundary? These questions may remain perpetually beyond empirical confirmation. In contemplating these cosmic contradictions, we encounter the humbling reality that our journey beyond the Milky Way may never reach a final destination, not because the universe has an edge, but because our ability to know it has limits fundamentally built into the cosmos itself. Chapter 6: Cosmic Misconceptions and Boundary Cases. As we traverse the vast expanses beyond our galaxy, we encounter not just physical phenomena, but human interpretations, stories we tell ourselves about what lies in the cosmic beyond. Some of these narratives, while compelling, don't align with our best scientific understanding. Perhaps the most persistent myth is that traveling beyond our galaxy means entering empty space, a perfect vacuum devoid of all matter. This misconception stems from photographs showing galaxies as island universes separated by apparent nothingness. In reality, the space between galaxies teems with diffuse gas, dust, rogue planets, stellar remnants, and vast plasma filaments. The intergalactic medium, while incredibly tenuous by earthly standards, contains most of the ordinary matter in the universe, a cosmic ocean hiding in plain sight. Another common misconception involves the edge of the universe. Popular imagery often portrays the cosmos as an expanding bubble with a definable boundary. What lies beyond this edge? The question itself contains a misconception about the nature of cosmic expansion. According to our best understanding, the universe has no center or edge in the conventional sense. Space itself expands everywhere at once, carrying galaxies along like raisins in rising bread dough. There is no outside to travel to, no boundary to cross. This concept challenges human intuition, which evolved to understand bounded spaces with clear insides and outsides. Our minds struggle to grasp a cosmos that might be infinite or finite, curved in higher dimensions like the surface of a hypersphere. Another persistent myth suggests that beyond our galaxy lies absolute darkness, a night sky without stars. While intergalactic space would indeed appear darker than our star-filled galactic view, distant galaxies themselves would be visible as faint smudges of light across the cosmic void. From truly intergalactic space, our Milky Way would appear as a luminous spiral, while other galaxies would dot the darkness like cosmic islands. The view would be sparse compared to our star-rich galactic perspective, but far from the absolute blackness often imagined. Science fiction frequently depicts intergalactic travel as simply a longer version of interstellar journeys. But the scales involved create challenges beyond mere distance. The closest major galaxy, Andromeda, lies 2.5 million light-years away, a gulf that transforms the nature of the journey itself. At the speed of our fastest spacecraft, reaching Andromeda would take tens of billions of years, longer than the current age of the universe. Even at significant fractions of light speed, the journey would span millions of years. requiring technologies far beyond current capabilities. Viral images often show Andromeda looming large in Earth's sky, suggesting our neighboring galaxy appears enormous but dim. These images, while based on actual relative size, mislead views about visibility. To human eyes, Andromeda appears as a small, faint smudge under dark skies. These images typically show what Andromeda would look like if its faint outer regions were as bright as its center, a visualization technique that, while scientifically informative, creates misconceptions about what our galactic neighbor actually looks like from Earth. Another common misconception involves the eventual collision between our Milky Way and Andromeda galaxies. Popular accounts often describe this as a catastrophic crash, with stars smashing into each other like cosmic billiard balls. In reality, galaxies consist mostly of empty space. When they merge, individual stars rarely collide. Instead, gravitational interactions gradually reshape both galaxies into a single elliptical galaxy. Our solar system will likely be thrown into a different galactic orbit, but remain otherwise intact. Some popular narratives suggest regions beyond our galaxy contain exotic dark galaxies, composed entirely of dark matter with no stars at all. While dark matter halos without significant visible matter may exist, they wouldn't appear as galaxy-shaped voids in space. True dark matter halos would be detectable only through their gravitational effects on surrounding matter or light. They wouldn't look like ghostly negative images of normal galaxies, an artistic conception that makes for compelling visuals, but misrepresents their actual nature. A persistent myth suggests that beyond the observable universe lies true emptiness, or nothingness. This fundamentally misunderstands modern cosmology. The observable universe is limited by light's travel time since the Big Bang, not by any physical boundary separating cosmos from void. What exists beyond our cosmic horizon likely resembles what we observe within it: more galaxies, more clusters, more cosmic web, extending perhaps infinitely. We cannot observe these regions not because they're empty, but because their light hasn't had time to reach us. Some speculative theories suggest our universe might be one bubble in a vast multiverse, but popular accounts often misrepresent this as different universes physically adjacent to ours, separated by some traversable barrier we might someday cross. In most scientific multiverse theories, other universes wouldn't exist elsewhere in our space, but in fundamentally separate spacetimes, potentially with different physical laws and dimensions. They wouldn't be locations we could reach by traveling far enough beyond our galaxy. The concept of rogue planets wandering interstellar and intergalactic space has captured popular imagination, sometimes depicted as Earth-like worlds drifting between star systems or galaxies. While such planets exist, those in intergalactic space would be extraordinarily difficult to detect. More importantly, without a star's energy, such planets would be frozen worlds far colder than Antarctica, with surface temperatures approaching absolute zero. Any oceans would be solid ice. Atmospheres would condense into frozen layers. They would not resemble habitable worlds. Another misconception involves the appearance of distant galaxies. Popular media often depicts them as we see them in telescope images: colorful spirals and ellipticals with clearly defined structures. But these images typically use false colors to highlight different wavelengths invisible to human eyes. To human vision, most galaxies would appear as faint grayish smudges. The spectacular colors in astronomical images represent scientific data visualization rather than what human travelers would actually see journeying beyond our galaxy. The cosmic microwave background radiation, the afterglow of the Big Bang visible in all directions, is sometimes misunderstood as a physical wall or barrier marking the universe's beginning. In reality, it represents the point where the universe became transparent to light, not a location in space. We observe this radiation coming from all directions, not because we're at the center of a cosmic sphere, but because every location in the universe was once part of the hot, dense plasma that eventually cooled to release this radiation. Misconceptions also surround the concept of cosmic voids, vast regions where galaxies are scarce. These aren't completely empty, but contain tenuous gas and isolated galaxies. They're not holes in the universe, but underdensities in the cosmic web, regions where matter is less concentrated. These voids form naturally through gravitational attraction. As matter clumps together to form filaments and clusters, it leaves behind regions with less material. Voids thus represent the natural counterpart to cosmic structures, not aberrations or evidence of something missing from the universe. Some accounts suggest intergalactic space harbors unknown forms of exotic matter or energy fundamentally different from what we observe in our galaxy. While dark matter and dark energy remain mysterious, evidence suggests they permeate all space, including our own galaxy. The space between galaxies doesn't contain fundamentally different physics from what exists within galaxies. The same forces and particles operate throughout the observable universe, though their distributions and densities vary across cosmic environments. A final misconception worth addressing involves cosmic distances and the limits of exploration. Popular narratives sometimes suggest that with sufficient technology, humanity might someday explore beyond our galaxy, mapping the cosmos through direct observation rather than telescope imagery. The scales involved render such exploration effectively impossible. Even at light speed, reaching Andromeda would take 2.5 million years. Exploring significant portions of even our local group of galaxies would require timeframes longer than human civilization has existed, possibly longer than our species might endure. These misconceptions don't diminish the wonder of what truly exists beyond our galaxy. If anything, the reality, a cosmic web of galaxy clusters and filaments stretching across billions of light years, shaped by invisible dark matter and expanding due to mysterious dark energy, exceeds the myths in grandeur and mystery. Chapter 7. The Cosmic Stakes of Our Intergalactic Perspective. What difference does it make? This journey beyond our galaxy. Why should we care about regions of space so distant we'll never visit them? The answer lies not in practical exploration, but in how this expanded perspective transforms our understanding of ourselves and our cosmic context. Consider navigation, not just through physical space, but through the landscape of scientific knowledge. By observing distant galaxies, astronomers constructed the cosmic distance ladder, a series of interlocking methods for measuring astronomical distances with increasing accuracy. This distance ladder begins with radar ranging in our solar system and extends through parallax measurements of nearby stars, standard candles like Cepheid variables in neighboring galaxies, and Type A, a supernova visible across billions of light years. Each rung of this ladder builds on a previous one, allowing us to measure the universe with remarkable precision. These measurements reveal the universe's expansion rate, its acceleration, and ultimately its age. Approximately 13.8 billion years since the Big Bang. Without observing beyond our galaxy, we couldn't have discovered dark energy or measured the universe's expansion history. We would remain confined to a much smaller conceptual universe, missing crucial evidence about cosmic evolution and destiny. Our journey beyond the Milky Way also revealed something profound about matter itself. The elements that comprise our bodies emerged from different cosmic sources across billions of years of galactic evolution. Hydrogen, the most abundant element, formed in the earliest moments after the Big Bang. Helium and trace amounts of lithium followed shortly thereafter. But heavier elements, carbon, oxygen, iron, and all the rest, required stellar furnaces to forge them through nuclear fusion. The heaviest elements emerged from violent stellar explosions and neutron star collisions. By studying distant galaxies at various stages of evolution, astronomers trace this elemental history, revealing how generations of stars gradually enriched the cosmos with the building blocks of planets and life. This cosmic perspective fundamentally changed how we understand our physical composition. As Carl Sagan famously noted, we are star stuff. Our atoms were forged in stellar cores and supernova explosions billions of years before Earth formed. But our journey beyond the galaxy revealed something even more profound. We are not just star stuff, but galaxy stuff. The complex interplay between stars, gas, dark matter, and supermassive black holes within galaxies created the conditions necessary for our existence. Understanding galactic evolution across cosmic time provides context for our own galaxy's history and future. The Milky Way has evolved through multiple mergers with smaller galaxies, a process that continues today and will culminate in the eventual merger with Andromeda billions of years hence. This galactic archaeology, pieced together by observing distant galaxies at different evolutionary stages, reveals our cosmic lineage, the sequence of events that led to our particular corner of the universe, developing the precise conditions needed for life to emerge. Our journey beyond the Milky Way also transformed our measurement of time itself. By observing the most distant galaxies and quasars, we extended our temporal horizon from thousands of years of human history to billions of years of cosmic evolution. This expanded time frame provides crucial context for understanding Earth's history. The 4.5 billion year age of our planet, once seemingly immense, represents merely a third of cosmic history. Galaxies had already been evolving for billions of years before our solar system formed. Our cosmic perspective also reveals the relative youth of complex life on Earth. While galaxies have existed for over 13 billion years, multicellular life on our planet emerged only about 600 million years ago, the most recent 4% of cosmic history. This temporal perspective provides a humbling reminder of our recent arrival on the cosmic stage. Yet it also highlights the remarkable rapidity with which consciousness has developed the capacity to comprehend the universe that produced it. Perhaps the most profound stake in our journey beyond the Milky Way involves the future, not just of humanity, but of cosmic evolution itself. By observing distant galaxies, astronomers discovered evidence for dark energy and the accelerating expansion of the universe. This discovery fundamentally altered our understanding of cosmic destiny. Rather than eventually collapsing back in a big crunch or expanding at an ever-slowing rate, the universe appears destined for eternal expansion, with galaxies accelerating away from each other into cosmic isolation. In the far future, trillions of years hence, galaxies beyond our local group will have receded beyond the cosmic horizon, their light unable to reach us due to cosmic expansion. Future civilizations arising then would observe an apparently smaller universe, with evidence for the Big Bang increasingly obscured. This realization carries a profound implication. We exist during a special epoch when the evidence for cosmic evolution remains observable. Future astronomers will have access to less information about the universe's origins and large-scale structure than we do today. Our responsibility to document and understand the cosmos thus takes on additional significance. The knowledge we gain by observing beyond our galaxy represents a cosmic heritage that future generations might otherwise lose access to as the universe continues its accelerating expansion. On more practical timescales, understanding cosmic evolution informs our assessment of existential risks. Observations of distant galaxies reveal the frequency of potentially civilization-ending events like nearby gamma-ray bursts, helping us evaluate threats to humanity's long-term survival. Our journey beyond the Milky Way also transforms our search for extraterrestrial life. By studying galaxies across cosmic time, astronomers can identify epochs and environments most conducive to life's emergence, narrowing the search for potential communicative civilizations. The discovery of thousands of exoplanets orbiting distant stars has revealed that planetary systems are commonplace throughout our galaxy and presumably throughout the cosmos. This abundance of potential habitats expands the possibilities for life beyond Earth. Yet the vast distances between galaxies create a sobering reality. Even if intelligent life exists in abundance throughout the cosmos, intergalactic communication would span millions or billions of years. Any conversation between galactic civilizations would transcend the timescales of individual species. This cosmic perspective doesn't diminish the significance of finding life elsewhere, it enhances it. Each instance of life would represent an independent experiment in evolution, providing crucial data about life's frequency, diversity, and resilience across cosmic environments. Perhaps most profoundly, our journey beyond the Milky Way confronts us with the ultimate fate of our cosmic home. In the distant future, stellar evolution will exhaust the gas needed for new star formation. Existing stars will gradually die out, leaving behind stellar remnants, white dwarfs, neutron stars, and black holes. Over incomprehensibly long timescales, quadrillions of years, these remnants will either escape their galaxies or spiral into central supermassive black holes. Eventually, even these black holes will evaporate through Hawking radiation, leaving an increasingly diffuse, cold, and dark cosmos. This heat-death scenario, while unimaginably distant, raises profound questions about meaning and purpose in a universe with a beginning and an end. If cosmic evolution proceeds from organization toward eventual disorder, what significance should we attribute to the brief flourishing of complexity and consciousness? As physicist Brian Cox eloquently noted, we are the cosmos made conscious. Our ability to comprehend the universe, to trace its history and project its future, represents something remarkable. Matter organized in such a way that it can contemplate its own existence and evolution. This cosmic awareness doesn't solve the riddle of meaning, but it transforms it. We are not separate from the cosmos observing it from outside. We are the means by which the universe observes and understands itself, a perspective that emerges only when we journey beyond our galactic boundaries. As we prepare to venture deeper into cosmic mystery, we carry this perspective with us, not as final answers, but as an evolving framework for understanding our place in a universe far vaster, older, and stranger than our ancestors could have imagined. Chapter 8: The Grand Cosmic Theories. As our journey takes us to the furthest reaches of observable space, we encounter fundamental questions about what truly happens when we leave our galaxy behind. Several comprehensive theories attempt to explain the universe's large-scale structure and ultimate fate, each with compelling evidence and lingering uncertainties. The standard lambda-CDM model represents our current cosmological consensus. This framework proposes that the universe began with the Big Bang approximately 13.8 billion years ago and has been expanding ever since. Its evolution governed by dark energy, lambda, and cold dark matter, CDM. According to this model, as we travel away from the Milky Way, we would encounter an increasingly sparse cosmic landscape. Galaxies would gradually become more distant from each other, with the space between them expanding at an accelerating rate due to dark energy's influence. In the far future under this model, most galaxies would recede beyond our cosmic horizon, their light unable to reach us because the space between expands faster than light can travel across it. Eventually, even our local group of galaxies would become isolated in an otherwise empty observable universe. This cosmic loneliness represents one of the model's most profound predictions. In trillions of years, future astronomers would see only a handful of nearby galaxies, with the rest of the cosmic story, including evidence for the Big Bang itself, faded beyond observational reach. While lambda-CDM successfully explains most observations, it leaves crucial questions unanswered. What is dark matter made of? Why does dark energy have its observed value? These mysteries have led some scientists to propose alternative cosmological frameworks. The conformal cyclic cosmology theory, developed by mathematician Roger Penrose, offers a dramatically different vision. This model suggests our universe represents just one eon in an infinite cycle of universes, each beginning with a Big Bang and ending with a highly expanded, low-entropy state. According to Penrose, when the universe expands to the point where all matter has decayed into radiation, the distinction between extremely large and extremely small scales becomes meaningless. This equivalence allows the end of one eon to seamlessly become the beginning of the next. If conformal cyclic cosmology proves correct, traveling beyond our galaxy would eventually reveal subtle patterns in the cosmic microwave background, scars from supermassive black hole collisions in the previous cosmic eon. Penrose claims to have identified such patterns, though most cosmologists remain skeptical. This cyclical model offers a profoundly different answer to what lies beyond our cosmic horizon. Rather than endless expansion into emptiness, it suggests our universe forms part of an eternal cycle of death and rebirth, with information potentially preserved across cosmic eons. A third framework, the emergent gravity theory proposed by Eric Verlinde, suggests gravity itself might not be a fundamental force, but rather an emergent phenomenon, similar to how temperature emerges from the collective motion of molecules rather than being a fundamental property. This theory reconceptualizes dark matter not as an undiscovered particle, but as a manifestation of gravity's emergent properties at galactic scales. If correct, what we interpret as dark matter halos around galaxies would actually represent modifications to gravitational behavior in low acceleration environments. For intergalactic travelers, emergent gravity would mean the apparent emptiness between galaxies might behave differently than expected. The gravitational effects we attribute to dark matter would arise naturally from the distribution of ordinary matter through space-time's elastic response. Each of these frameworks makes different predictions about what happens as we journey farther from the Milky Way. The Standard Model foresees cosmic acceleration leading to eventual isolation. Cyclic cosmology suggests evidence of previous universes. Emergent gravity reimagines the very forces shaping cosmic structure. But perhaps the most transformative theory regarding what lies beyond our galaxy comes from inflation. The idea that the most transformative theory regarding what lies beyond our galaxy comes from inflation. The idea that the universe underwent exponential expansion in its first fraction of a second. This concept, introduced by physicist Alan Guth, helps explain the universe's uniformity and structure. Inflationary theory, however, contains a startling implication. Our observable universe might be just one bubble in a vastly larger multiverse. In this scenario, the process that triggered inflation continues eternally in some regions while stopping in others, creating countless pocket universes. If this eternal inflation model is correct, then sufficiently far beyond our galaxy, beyond our observable universe, would lie other cosmic bubbles with potentially different physical laws, dimensions, and fundamental constants. These regions would forever remain beyond our observational reach. The multiverse concept fundamentally transforms our understanding of what lies beyond the Milky Way. The answer would no longer be merely more galaxies and more space, but potentially other universes with fundamentally different properties, an infinity of cosmic possibilities. Yet we must approach these theories with appropriate scientific humility. The multiverse remains a theoretical framework rather than an established fact. Similarly, cyclic cosmology and emergent gravity represent minority viewpoints within the scientific community, albeit ones proposed by respected researchers. The Lambda-CDM model, despite its mysteries, continues to provide the most comprehensive explanation for our observations. Its prediction of an accelerating cosmos that eventually isolates galaxies remains our best understanding of what happens when we travel beyond our galaxy. What unites these competing theories is their attempt to explain observations that have fundamentally changed our cosmic perspective. A century ago, astronomers debated whether the Milky Way constituted the entire universe. Today, we contemplate multiple universes and cosmic cycles spanning eternity. This theoretical evolution reflects our expanding cosmic horizon. As our instruments peer farther into space and thus further back in time, they reveal new phenomena that challenge existing frameworks and inspire new ones, continuously refining our understanding of what exists beyond our galaxy. Perhaps most remarkable is that these competing theories, despite their differences, all emerge from the same observations, the same light from distant galaxies, the same cosmic microwave background, the same gravitational phenomena. They represent different interpretations of the same cosmic evidence. This multiplicity of viable explanations reminds us of the provisional nature of scientific knowledge. Our understanding of what lies beyond the Milky Way will continue to evolve as new evidence emerges and new theoretical frameworks develop to explain it. For now, we can say with confidence that beyond our galaxy lies a cosmic web of galaxy clusters and filaments stretching across billions of light years, embedded in an expanding space governed by forces we only partially understand. Beyond that, we enter the realm of competing theories. As we contemplate these grand cosmic frameworks, we must remember that even our most comprehensive theories represent maps rather than territories, human constructs designed to make sense of a universe whose full reality may exceed our capacity to comprehend. Chapter 9: Cosmic Frontiers and New Windows. Our journey beyond the Milky Way continues to evolve as new instruments and observational techniques reveal previously hidden aspects of the cosmos. These technological advances function as extensions of our senses, allowing us to perceive the universe in ways impossible just decades ago. The James Webb Space Telescope, launched in 2021, represents humanity's most powerful eye on the distant universe. Operating primarily in infrared wavelengths, Webb can peer through cosmic dust clouds that block visible light, revealing star formation in unprecedented detail across cosmic history. Perhaps most significantly for our journey beyond the Milky Way, Webb can observe galaxies from the universe's infancy, just a few hundred million years after the Big Bang. These observations reveal how galaxies initially formed and evolved, providing crucial context for our own galaxy's history. Early Webb observations have already yielded surprises, including fully formed galaxies appearing earlier in cosmic history than our models predicted. These discoveries challenge aspects of our understanding about how galaxies assemble and evolve across billions of years. As Webb continues its mission, it will map the distribution of dark matter by observing how galactic light bends around invisible mass concentrations, a phenomenon called gravitational lensing. This technique transforms dark matter from theoretical necessity to mapped reality, revealing its cosmic architecture. Complementing Webb's vision, ground-based observatories continue to expand our cosmic perspective. The upcoming Extremely Large Telescope, ELT, with its 39-meter primary mirror, will gather 13 times more light than any existing optical telescope, revealing fainter, more distant objects. This immense light-gathering power will allow astronomers to directly observe the cosmic web, the filamentary structure of dark matter and gas connecting galaxies across billions of light years. These observations will reveal the universe's largest-scale structures, showing how galaxies cluster and align. Beyond traditional astronomy, entirely new observational windows have opened. Gravitational wave detectors like LIGO and Virgo sense ripples in spacetime created when massive objects collide, providing information impossible to obtain through electromagnetic radiation alone. These gravitational waves pass through cosmic dust and gas unimpeded, carrying information about some of the universe's most energetic events: black hole mergers, neutron star collisions, and potentially phenomena we haven't yet anticipated or understood. The first detection of gravitational waves in 2015 confirmed a century-old, prediction from Einstein's theory of general relativity. But perhaps more significantly, it inaugurated a new era of multi-messenger astronomy, where cosmic events can be observed through complementary signals. In 2017, astronomers detected gravitational waves from colliding neutron stars while simultaneously observing the electromagnetic radiation produced by this collision. This multi-messenger observation revealed these cataclysmic events as the cosmic forges where many heavy elements are created. Another observational frontier involves neutrinos, nearly massless particles that interact so weakly with matter that trillions pass through your body every second. Specially designed detectors buried deep underground or in Antarctic ice can capture rare neutrino interactions, revealing their origins. Unlike light, which can be blocked or scattered, neutrinos travel through the universe virtually unimpeded, carrying information directly from cosmic events like supernova. They provide a pristine signal from processes hidden from traditional telescopes. The IceCube Neutrino Observatory at the South Pole detected high-energy neutrinos originating from outside our galaxy, opening yet another window on the cosmos. These particles allow us to observe accelerators of cosmic rays and other energetic phenomena invisible to conventional astronomy. Together, these observational advances create a more complete picture of what exists beyond our galaxy. The universe revealed through multiple messengers, light across all wavelengths. Gravitational waves, neutrinos, proves far more dynamic and interconnected than previously understood. New observations consistently reveal the universe as more complex and puzzling than our theories anticipate. Galaxies appear fully formed earlier than expected. Cosmic structures extend beyond predicted scales. The cosmic expansion rate, measured through different methods, yields inconsistent values. These tensions between theory and observation, far from representing failures, drive scientific progress. They identify precisely where our understanding remains incomplete, guiding future theoretical development and observational priorities. Perhaps the most significant mystery emerging from new observations involves the universe's expansion rate, the Hubble constant. Measurements based on the cosmic microwave background suggest one value, while observations of nearby galaxies indicate a significantly different one. This Hubble tension defies simple resolution. If confirmed through additional measurements, it might require fundamental revisions to our cosmological models, perhaps introducing new particles, energy forms, or even modifications to our understanding of gravity itself. New observations also reveal the universe's large-scale structure in unprecedented detail. Galaxy surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the cosmic web, a network of filaments and voids spanning billions of light years. This web-like structure emerged from quantum fluctuations in the early universe, amplified by gravity over billions of years. Its pattern contains information about dark matter, dark energy, and the universe's early conditions, a cosmic fossil record we're still learning to interpret. Recent observations of the cosmic web reveal that galaxies are not randomly oriented, but tend to align with these filaments. This alignment suggests a cosmic choreography, with galactic rotations influenced by the large-scale structure surrounding them, a dance played out across billions of years. Our journey beyond the Milky Way thus reveals not isolated objects in empty space, but an interconnected cosmic ecosystem, where matter flows along filaments between galaxies and galaxy clusters, driven by gravity and cosmic expansion in intricate balance. New observational techniques also allow us to map the temperature and composition of intergalactic gas, the material filling the space between galaxies. This gas constitutes the largest reservoir of ordinary matter in the universe, yet remained largely invisible until recent technological advances. Through specialized X-ray observations and the Salyunov-Zeldovich effect, which, detects distortions in the cosmic microwave background caused by hot gas. Astronomers can now map this intergalactic medium, revealing how galaxies interact with their environment. These observations show galaxies breathing, inhaling hydrogen gas that fuels star formation and exhaling heavier elements through supernova and galactic winds. This cosmic respiration creates a chemical enrichment cycle extending far beyond individual galaxies. Perhaps most surprising, recent observations suggest the intergalactic medium contains far more complex molecules than previously thought possible in such harsh environments. These include organic compounds, the chemical precursors to life, distributed throughout intergalactic space. The implications are profound. The chemical foundations for life exist not just within galaxies, but throughout the cosmic web. While this doesn't guarantee life elsewhere, it suggests that basic ingredients are widespread rather than confined to rare, specialized environments. As we synthesize information from these diverse observational windows, our journey beyond the Milky Way reveals an increasingly dynamic universe. Galaxies collide and merge. Supermassive black holes eject matter at nearly the speed of light. Intergalactic gas flows along invisible cosmic filaments. This dynamism extends to the universe's largest scales. Whole galaxy clusters collide in cosmic train wrecks lasting billions of years. Vast bubbles of radiation expand from energetic galactic nuclei. The cosmic web itself evolves as dark energy accelerates universal expansion. What emerges from these new observations isn't merely a more detailed map of what exists beyond our galaxy, but a transformative understanding of the cosmos as an integrated, evolving system, one where events in seemingly empty intergalactic space influence galactic evolution and vice versa. Perhaps most significantly, our expanding observational horizon continually pushes back the frontiers of knowledge, revealing phenomena that challenge existing theories and inspire new ones. This cycle of observation, theorization, and further observation drives cosmic understanding forward. As we stand at the threshold of new observational capabilities, from space-based gravitational wave observatories to 30-meter class telescopes, we prepare for another transformation in our understanding of what exists beyond our galaxy, one potentially as profound as any that came before. Chapter 10. Beyond the Cosmic Horizon. We've journeyed conceptually from our galactic home across billions of light years, through galaxy clusters and cosmic voids, to the edge of the observable universe. Now we must address our original question directly. What happens if you keep traveling away from the Milky Way? The answer emerges from everything we've explored, a synthesis of observational evidence and theoretical frameworks that reveals a cosmic story both grander and stranger than our ancestors could have imagined. It's a story that transforms not just our understanding of space, but of time itself. As you travel beyond the Milky Way, you first encounter our local group, a collection of over 80 galaxies gravitationally bound together, dominated by Andromeda and the Milky Way. This island in space spanned roughly 10 million light years and represents our immediate cosmic neighborhood. Continue outward, and you enter a region of cosmic expansion. Here, space itself stretches, carrying galaxies away from each other. This expansion doesn't have a center. It occurs everywhere at once, like the surface of an inflating balloon where every point moves away from every other point. At distances of tens of millions of light years, you encounter galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity. These clusters form the nodes of the cosmic web, connected by filaments of gas dust and dark matter spanning millions of light years. Travel further, to hundreds of millions of light years, and larger structures emerge, superclusters containing multiple galaxy clusters, arranged in vast sheets and filaments surrounding nearly empty voids. This cosmic web extends across the observable universe, encompassing billions of galaxies. At these scales, the universe appears remarkably uniform when averaged over large enough volumes, a property cosmologists call homogeneity. This uniformity represents one of the great puzzles of cosmology, as regions on opposite sides of the observable universe had no time to interact since the Big Bang. Continue your journey to billions of light years, and you approach the observable limit of our universe. Not a physical boundary, but a horizon beyond which light hasn't had time to reach us since the Big Bang. This cosmic horizon currently extends about 46.5 billion light years in all directions. Here we encounter a profound revelation. As you approach this horizon, you're not just traveling through space, but back in time. Light from these distant regions shows the universe as it was billions of years ago. Younger, hotter, and denser, with galaxies in earlier stages of formation. At the very edge of observability lies the cosmic microwave background, the afterglow of the Big Bang itself. Beyond this point, the early universe was opaque to light, a hot plasma where photons couldn't travel freely. This represents the earliest moment we can directly observe. But what if you could continue beyond this observable horizon? What would you find? Here, theoretical physics must guide us where direct observation cannot reach. According to our best models, you would discover more of the same. More galaxies, more clusters, more cosmic web. The universe likely extends far beyond what we can observe, potentially infinitely. This extended cosmos would, on large scales, resemble our observable portion, governed by the same physical laws and containing similar structures, though with endless unique variations in the details. However, quantum fluctuations during cosmic inflation may have created regions with different fundamental constants, or even different physical laws. These regions would lie far beyond our observable horizon, forming essentially separate universes within a vast multiverse. This brings us to a humbling conclusion. If you keep traveling away from the Milky Way, you eventually reach regions from which light has not yet had time to reach us. Continue further, and you might encounter regions forever beyond observation due to cosmic acceleration. The answer to our question thus contains a profound paradox. We can scientifically infer what exists beyond our observational reach, but we cannot directly confirm these inferences. The cosmos beyond our horizon represents a realm of informed speculation rather than empirical certainty. This limitation isn't merely practical, but fundamental, built into the structure of spacetime itself. Cosmic expansion creates boundaries to what can be observed or reached, even in principle. Some regions of the universe will forever remain beyond our cosmic horizon. Yet even with these limitations, our journey reveals something remarkable. The universe transitions from the intimately observable, our galactic home, to the fundamentally unobservable, with no clear dividing line between. The cosmos fades gradually from empirical certainty into theoretical inference. This gradual transition reflects how scientific knowledge itself develops, not through sudden leaps from ignorance to certainty, but through progressive refinement of understanding, with theories extending beyond direct observation and observations continuously testing theoretical predictions. In a profound sense, what happens when you keep traveling beyond the Milky Way is that you encounter the limits not just of our observational capabilities, but of knowledge itself. You discovered the boundary between what can be known through direct observation and what can only be inferred. Yet this boundary isn't fixed, but expanding. As light from increasingly distant regions reaches us, our observable universe grows. Each passing year adds about 87 million light-years to the diameter of our cosmic horizon, continuously revealing previously unseen portions of the cosmos. Simultaneously, cosmic acceleration works against this expansion of our horizon. Regions sufficiently distant are carried away faster than their light can reach us, permanently placing them beyond observation. Our observable universe thus has both an expanding edge and an ultimate limit. This cosmic ballet between revelation and concealment defines our relationship with the universe beyond our galaxy. The cosmos continuously reveals itself to us through light traveling across billions of light years, while simultaneously ensuring some regions remain forever hidden. Perhaps most profoundly, our journey beyond the Milky Way ultimately leads not to a place, but to a perspective, an understanding of our cosmic context that transforms how we see ourselves and our place in the universe. We exist at a particular moment in cosmic history, able to observe both the universe's past through distant light and infer its future through physical laws. In answering what happens if you keep traveling beyond our galaxy, we discover that the journey itself transforms the traveler. We emerge with a deeper appreciation for both the comprehensibility of the cosmos through scientific inquiry and the fundamental limits to what can be empirically known. As our journey beyond the Milky Way concludes, we return to our galactic home with transformed perspective. We've traveled conceptually across billions of light years, through galaxy clusters and cosmic voids, to the very edge of the observable universe, and contemplated what might lie beyond. This cosmic perspective doesn't diminish our significance, but contextualizes it within a grander narrative. We are collections of atoms forged in stellar furnaces, arranged into consciousness, capable of comprehending the very stars that created us, the universe aware of itself. Our brief moment of cosmic awareness exists within a universe spanning billions of years and light years. Yet this very brevity makes it precious, a rare instance where matter has organized itself sufficiently to contemplate its origins and place within the cosmic tapestry. As you drift to sleep tonight, carry with you this cosmic perspective, not as a burden but as a gift, an invitation to see your daily concerns within a larger context that doesn't eliminate their importance, but nestles them within a greater whole. Join us again soon for another journey through the sleeping cosmos.